Welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm finding out what microchip is in the world of digital signal controllers. My guest today is Alexis Alcott. Alexis is the Associate Director of Marketing at Microchip Technology. Welcome to the podcast, Alexis.
Thank you so much for having me today.
It's great. So to start off with, can you just explain a little bit about what you do at Microchip and what your role entails?
Absolutely. I lead our marketing team for the dsPIC digital signal controller business unit. And so that includes things like product definitions, ecosystem investments, our outbound marketing initiatives like promotions, as well as our business development for focus accounts and emerging markets.
So digital signal controller, that's different from a microcontroller, isn't it? Can you explain what the difference is?
Yeah, certainly. So basically, if you look at the whole landscape for controllers, the 8-bit space comes from a hardware centric viewpoint, where it's typically a single function, low power, low cost implementation. And then if you go all the way up into the 32-bit realm, it tends to be more software centric. There's a lot of connectivity, communication stacks, and so forth. And so the digital signal controller really kind of sits in the middle, where we maintain the hardware-centric nature of an 8-bit microcontroller with really low latency and fast responsiveness, but add in the ability to have some additional very specialized algorithms and performance.
So presumably that's around, I guess the name says it all, controlling things in real time. So running an algorithm that then lets you control, for example, what would it be, a motor or something?
Yes, exactly. So anything that needs very fast responsiveness, we call it low latency, but that's kind of a fancier term. Anything that needs to interact with the real world in a fast way. So motor control is a perfect example. Another one would be digital power conversion. Another area would be advanced sensing. So if there's some type of sensing input that you need to act on in a very fast way.
Okay, so these controllers, they're optimized for responsive, so low latency, but presumably they also have some capabilities on the math side to run those algorithms.
Yes, the CPU tends to have a lot of very specialized capabilities. And it's really the special sauce is how the core interacts with the peripherals. So there's a lot of integration between things like the analog to digital converters that bring the data in to the core and then to the pulse width modulation that help drive different systems. So that can be helpful in applications like fans or pumps or actuators, or even in a really fast segment that we see in the digital power space with servers and data center power supplies.
That makes a lot of sense. And what about, high reliability type applications? Can you use DSCs where there's functional safety requirements or where there's other criteria like in automotive?
For sure, that's an area these parts particularly are designed for. Some products are designed for broad markets, and then they bring pieces of the portfolio into automotive qualification. For example, with the digital signal controllers, the automotive qualification goes into all of the products that are designed, and that is a primary market. High reliability is a really big piece of the equation. A lot of these parts go into safety critical applications that require full redundancy, and you need to ensure that if something fails in the system, that it's going to fail in a safe as possible way.
That's really cool. I mean, it sounds like that there's quite a broad range of applications. So can you break them down maybe into some broad categories and then perhaps give some examples of specific applications in those categories?
Yeah, absolutely. So one part is within the e-mobility segment. And so here we've got either motor control or power conversion type of applications that go into electric vehicles like onboard chargers. There's a lot of different power levels that need converted within an electric vehicle. So there can also be DC to DC conversion. Another thing people don't think about in an electric vehicle is without the motor, of the combustion engine, you don't have heat. And so all of a sudden, you need to build in a full HVAC in order to heat the car. You can't just take that engine heat. So now there's the need for HVAC compressors in electric vehicles. And then in general, electric vehicles tend to have just more motors. So more compressors, more fans, more pumps and actuators. So all of those are example applications. Then if you take beyond e-mobility into just the automotive space, people are still buying a lot of traditional vehicles as well. The whole world hasn't shifted all the way over to electric vehicles just yet. And so there's additional innovation happening within the car, things like wireless charging of cell phones and different devices. So the digital signal controller can help with that type of power conversion application to charge your phone while you're driving. Another segment that we see a lot of innovation in is sustainability. So people are talking at a high level about, what we can do to reduce our global emissions and make sure that we have the most responsiveness to the supply chain needs. And one big piece to that is in high efficiency motor control. So if you look overall, there's so many motors in the world, they actually consume about half of the world's electricity. So by increasing the efficiency in motors, that can be a very big, important application, as well as things that are more traditional in the sustainability realm, like solar microinverters or energy storage systems. And then the last area I would touch on for application spaces is in the data center space. So if you think about things that we do to store information in the cloud, all of that has to get stored somewhere. And so the data center industry is really booming. And then you add AI into the equation, you get even more data center needs. And so the digital signal controllers are a key component in the power supplies for all of those data center servers.
And it sounds to me like a lot of these applications are probably growing quickly. I guess the quest for sustainability and energy efficiency must be one of them.
Definitely. And I think energy efficiency is something people care about across all of these market segments. So I think there's a lot of focus from our clients and from end consumers to reduce energy usage. People want to have a supplier that cares in this area, and the products that Microchip has can help enable a pretty big impact there. If we dive just into the motor control space, people are upgrading their motors to more efficient motor types. They're using more variable speed and higher end algorithms to reduce that. And overall, those efficiencies can go a long way.
And what about the design challenges you're addressing? Are there specific things that engineers are trying to achieve that digital signal controllers are particularly good at doing?
There are, and one example would be in the size of various end applications. So we're seeing people wanting to mount the actual motor control board on the back of the motor itself. And so board space constraints is a design challenge that a lot of people face. And we have some products within the portfolio that add additional integration so that you can reduce the overall component count in your motor control design and make that very small form factor. One example would be cooling fans or oil pumps within a car. They're trying to fit those motors and those controls into very small form factors. Another example would be in the consumer electronics area, or more like the appliance market, where you have like a cordless vacuum cleaner. And they're so light and they're so small, there's only so many places you can actually put a board in those. And so fitting those electronics into the handle or into a very small space becomes important. Other design challenges are just the overall software complexities. So you add things like functional safety, you add connectivity, you need to add security into the equation. And so all of a sudden, what used to be a simple, small application code base gets much, much larger and requires quite a bit more code space to solve the same problem. And then I touched on security, but I think that alone is a very large design challenge many of our clients face is, it just because they're good at building whatever their application is, doesn't mean they have security expertise. But now that that design is connecting into other systems, it's important to add security into the system so they don't become a threat for any kind of a cyber attack.
That's fascinating. It sounds like there's a lot of different things, driving greater use of digital signal controllers. One thing I'm interested to know, what's the portfolio of products like? And maybe how would that, compare to, say, classic microcontrollers?
Well, the first dsPIC digital signal controller from Microchip was introduced way back in the early 2000s. I think it was 2001. And there have been several generations of improvement since then. Each generation tends to increase the performance, the precision, the accuracy, and also the amount of memory. But through the years, and all those innovations and changes, we remain true to the original intent that really the superpower or the differentiation is the real-time control. And so whether the performance needs that you have in your application are for the very high end, we have parts all the way up to 100 megahertz with multiple cores that can give, a very high-end application. Or there's, other products in the portfolio that, are smaller and more cost sensitive. So I think there's, thousands of different SKUs within the portfolio at this point in different peripheral configurations, different amounts of program memory. So we continue to try and make sure that there's products to fit that breadth of requirements from small to large.
And presumably, like MCUs, quite a large selection of peripherals that are integrated as well.
Exactly. So the peripherals can be anything from just regular digital type of communications. These compared to regular general purpose microcontrollers, these products tend to have higher end analog integrated. The A to Ds are higher performance, more precision, and the PWMs themselves are very fast, down into the picoseconds of resolution. We're also seeing a trend that the amount of program memory that is required in many real time control applications has gone up significantly from the last generation to what we have in production today. And some of that is fueled by the need for functional safety. So, diagnostic libraries, redundancy, things like that for safety compatibility. Also, for some of these parts that go into the automotive space, there's certain automotive softwares that are required. Many automotive customers use something called AutoSAR that tends to increase the software demands quite a bit.
And one thing I'm interested, you're talking a lot about real-time control. What's the impact of AI or machine learning in this space?
And that's an exciting area. And I think we're just in the infancy of seeing how that will play out. But within motor control, I think it'll be interesting to see one use case that clients talk about is in predictive maintenance. Now, I live in the Phoenix, Arizona area, and so the idea of our air conditioning going out in the summertime when it can be very very hot here is something we all want to avoid. And so if I could get some notification that my air conditioning was going to go on the fritz and start to create issues a day, a week, sometime before, so I could get maintenance to do that, that would be a best case scenario. And you can take that same type of approach into a factory setting. If a motor is going to fail at some point, that can impact the efficiency and the output of a factory. So that's definitely one interesting use case for motor control. Another one that may even be more pragmatic is in using AI type algorithms for the development itself. So having some automated tuning for the motor parameters. Motor parameters, you usually tune an algorithm for what the parameters in the motor is when you first design it. But over time, that motor, runs down or the parameters could change. So you could do some tuning in real time to optimize the efficiency of that motor application. So that could be interesting. And then in the data center space, AI and ML is going to be just a huge impact in the number of data centers that are required to support all of the AI data and infrastructure. So typically for us, our digital power conversion parts are going into maybe 15 kilowatt type racks. And now with the AI, the amount can increase up to 50 kilowatts very easily. And it can add in some additional requirements as well with security features and things like that. So the overall impact for AI and ML is exciting. I think it'll create a lot of innovation and opportunity.
And I think, this is really interesting. There's a lot of things driving more complexity. Obviously, the digital signal controllers, they're unique to Microchip. But what other Microchip strengths are brought to the digital signal controller market to help engineers?
So we talked a little bit already about the silicon itself. And so I think that the silicon has the right requirements to do the job. But a lot of the strengths really rely in the supporting development ecosystem. We always say having the right part is great, but it's not sufficient. You need more. And so we tend to work and make big investments into the hardware tools, the software algorithms. Parts are supported with the ecosystem of MPLab integrated development tools, as well as there's some specialized tools for the digital signal controllers, like, for example, Motor Bench development suite is a GUI that runs on your PC, and it helps with some of the commissioning of the motor parameters. And there's other tools like that for other type of products. But there's certainly a big need there to have the right algorithms and tools available. We also take, for certain key markets, we take not just the digital signal controller, but all the surrounding components for a design and turn those into reference designs. And our goal there is really to have kind of a proof of concept and a starting point for someone building out things there to get them maybe 80% of the way. And then they can add, their differentiation with that final 20%. A few examples of reference designs that we have for the digital signal controllers. One would be a refrigerator compressor, or another would be an e-scooter, or even an automotive cooling fan. We're certainly not building a reference design for a full refrigerator or a full car, but we take that piece of the equation and kind of build out that function that somebody can use in their end design. And the dsPIC's often kind of the anchor device or the heart of the system, but it's surrounded by a lot of other pieces. So there'll be, MOSFET drivers, power management chips, communication or connectivity, memory, and clock and timing, lots of other microchip content. So we put all that together in more of a full system solution.
And this is the TSS, the total system solutions I keep hearing about whenever I talk
Yes.
to business units. It's
hmm
you're working presumably with other business units to build these complete solutions.
We are. We're working closely to build the reference designs and define those, as well as just aligning our roadmaps of what new products need to be defined. And we work closely with many of the business units and product lines, but especially with our analog business unit. We work closely with them, and we've even built some joint products together that use some of their MOSFET drivers and communication stacks like CAN transceivers and things like that, integrating those with our digital signal controllers in a single package for some of those space constrained applications that we talked about earlier. We also work closely with our silicon carbide business unit. I think if you look at the EV market in particular, silicon carbide and dsPIC kind of go hand in hand in a lot of those power applications. Other examples of business units we work closely with, there's a touch business group. And so we support a lot of customers with robust touch in automotive applications. And so in areas like that, we coordinate closely on reference designs and go to market for applications in e-mobility, sustainability, and other key growth markets.
That's amazing. That's great. How many different business units you're working with and how many different technologies are actually integrated. I really appreciate your time, Alexis. One of the things we always ask before we finish the interviews is to get a little bit of advice. So, do you have a bit of favorite engineering advice you could give to listeners?
Oh, that's a great question. I can think of two things. The first one would be always leave headroom or buffer in your design. You go into a design and you think you know all the requirements, and then there's always just one more feature or one more thing that you want to add as you get closer to the finish line. And I've just seen too many clients just run out of headroom and they just need a little more memory or a few more IO pins. So I think that's one piece of advice. And then, especially for newer engineers, don't be afraid to ask for help. I think Microchip, for example, has a huge install base of code examples, reference designs, but also a community. There's forums out there, and people like to help each other be successful and share in the knowledge they have. So, asking for help is something engineers aren't necessarily known for being good at. And I think that there's a big benefit there.
That's awesome. That's great advice. I love the asking for help. So, Just to summarize, I mean, I feel like we've covered a huge amount of information about digital signal controllers today. Is there one thing you'd like people to take away from the podcast and really remember about the technology?
dsPIC is real-time control. It's perfect for applications that need motor control, power conversion, or advanced sensing, anything with low latency and safety critical applications.
I mean, I'm excited about the dsPIC family and digital signal controllers. If people are listening and they'd like to learn more about the products, where's the best place to find more information?
The best place as a jumping off point would be microchip.com/dsPIC or videos on our YouTube channel at Microchip Technology. You can reach out through our web team or your local sales office, but we really would love to hear from people and see how we can help with their next design.
That's amazing. And obviously, as you're a real expert on the technology, if listeners to the podcast have any questions, is there a way they could get in contact with you to follow up some of the things you've talked about?
Sure thing. Yeah, feel free to connect on LinkedIn, or you can send me an email at alexis.alcott@microchip.com. I certainly don't have all the answers, but I can get you in touch with the people that do.
That's amazing. Alexis, thank you so much for your time. I really appreciate it. And also for telling us all about what Microchip is in the world of digital signal controllers.
Thanks so much. It was a fun discussion.
Thanks for listening to the Microchip is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip is podcasts and our new Beyond the Microchip podcast series.